Hi there. The first time I read this, the prequel to the questions, I didn't understand one word. And first, that we have an analogy, I don't know. They are abelian groups, both of them, but I know of no analogy. And I do remember problem 11. Maybe I made a trick solution, but if they suggest taking a limit within a discrete field, I made that connection the second time I read it, and then I said, now we know for sure there is life on Saturn's moon Io, and it has landed on Earth. Well, the third time I said, okay, the problem starts here. Let L be a prime not equal to P, and suppose FQ contains all lth roots of unity. That is, I need to verify for myself that those two conditions are equivalent. I think the key is, we'll just say it not, that the multiplicative group of FQ is cyclic. So we choose a generator G, and since it has Q minus 1 elements, we know that G to Q minus unity is the unit element. And now if Q is equivalent to L modulo 2, then we can insert that here. Now what's the point of that? Well, let's do that. So that's the generator to LA equals unity. Now what should we prove? That it contains all the roots of unity? No, lth roots. So that means that G to A is an lth root. Then what about 2A, 3A, 4A up to LA? So I want all of this to be distinct. And then, of course, they are roots of unity. AL minus 1 is actually less than L. no, what is it? If we subtract a here, q equals L minus 1 times L plus A, so it's Q minus A plus 1. That doesn't quite make sense to me. I claim that these are distinct, and it's L minus 1 roots, and then we have G to naught as well. So that's the L roots of unity. The Lth root of unity. Next, assume that all of the roots let's call them omega, and this one being unity, of course, lies in FQ. And they are all equal to the generator in some power, say A, and that means that when we take it to nth power, we get unity. That's d to AL and then this must be a multiplum of Q minus 1 . Now that is wrong, a multiply of Q minus 1. Oops, this should be unity. It should be quite analogous, or the opposite of what I've done up here. I can't see right now why it doesn't add up. So I'll just take a break and look at the algebra here, and then I'll tell you what I found. We go from here to here, and this means that this equation means that x divides AL, thus Q equals AL plus 1 and we needed to show that it was equivalent to 1 modulo L. So that means I need to show that x divides A. So could x be a power of or contain the prime L? That would be logical from this equation. Oh no, because then G to A. Now what did I think here? So may L divide x. No. Yeah, no, my God. I thought I had it. I need another break. I found we need a little technique here. There are some powers. Oh, now we have that again. Take a new page. There are some powers, G to A, that give nth root of unity. They form an ideal within the integers. Multiplying two roots of unity adds them and putting it to some power, it still is an nth root of unity. So that means we have a generator. Let's call that A. And then when we take 2A, 3A, and then at some time we pass Q, or Q minus 1, and then Q. And if we do not hit Q minus 1, if we hit before, then the other one, the next one, will be smaller than Q minus 1 plus A. Because this guy is smaller than Q minus 1, and we add A each of them. So that means that we hit exactly Q minus unity. And that means that for some integer, it gives Q minus 1. So that's the conclusion. That was what I hoped I could make today. No, actually I hoped I could show number A here. The splitting field has either degree 1 or L over, still assuming this holds, of course. So let's see if I can write now. No. I found a trick one day, but I don't know what it was. Now, we may have one lth root of L. So assume that x to the lth equals a. Then all the guys, what do we call them? All the roots of unity, L roots of unity, are also lth roots of a. Oops. Must be x. So in this case, for x in FQ, then all lie in FQ. If not, then I claim that x, omega 1x, up to omega L minus 1x well, they are all roots, so that means that FQ extended with x is the splitting field. And we have the Galois group I need to double these, has exactly n elements. No, it was L elements. So therefore it's order L over. It's splitting field, so it's Galois, and it has exactly L elements. If there were, say, another one, L plus 1, then the fraction between the two would be an lth root of unity. So that's relatively easy. Hi, ready to start on part B. As you probably have divined, I find this problem very out of this world. So my first instinct is to make some examples. And I just will make them blue examples. Do P equals 2, like Q equals 4. Then L may be 3, Q, C, yeah, equals 8. Then L may be 7. In both of these cases, we have, well, all elements in FQ have order 3, except unit, of course, and order 7, except naught, of course, on the null element. Then we get to 16, where we have two possible choices of L. If we have a generated G, then G to the 5th will have order 3, and G to the 3rd will have order 5, and generate the group of points of order 5. (32) is trivial. Then 64, that's 2 to the 8th. Then L may be 3 or 7. It's 9 times 7. 63 equals 9 times 7. And that means that we have, if we have a generated G, then G to the 7th has order 9, that's interesting because that means that in F64 we have not only elements of order 3 but also of order 9. That made this somewhat more reasonable. It must be m prime up here, which is less than or equal to m. So already here, if we take m equals 1, then we have a 3 squared root of unity in FQ itself, to L to the naught. If we set L to the m to naught, it says that L roots, Lth roots of unity spans FQ itself. So I believe it's m prime here. Yeah. And that we already know from the intro. I take this as a sign that it's time to do a proof by induction. Let's prove this by induction. So we shall use part A with A equals unity. And what is the induction step? Let's write span as if it's a vector space. Generate is probably the more right word. Now I do it again. Where m prime may either be m or m minus 1. No, I probably can't read that. We assume that this guy is generated by the LM roots And that means that q to L n minus first is equivalent to unity modulo L to m, modulo L to m. So q to L that's the L to m to Lth roots. And we have to prove that the roots lie in this field. So what I would like to prove is that this implies q to L in mth is equivalent to unity modulo L to m plus 1. So let's see if we can do that. And then this guy, how can we get that? I think we should put it to the Lth power. And it's also equal to x times L and m plus unity to the Lth. And we use the binomial theorem. This is an I. When I is naught, we get unity, and when I is larger than or equal to 1, we get a factor L here, because it's a prime, and L to the mth in some power, which is at least L. So you can put this outside the parenthesis and then get a lot of numbers, integers in here. What have I proven? I think I have proven that if this guy contains these roots, then the L to m plus 1th roots lie in this guy. And the splitting field, now we use part A, the splitting field of x to what? This is only for a prime, and I need it for a prime power. No, we do not. It's actually, we can actually use it L to m minus 1th root of unity. We know that the field, I forgot the word, the splitting field of this equation that was the roots of order m plus 1. Modulus the field has order 1 or L. Now we are back to some basic calculation here. I don't know why I find it so difficult. I have already done it up here. Actually, where did I do it? Oh, that was on the first page. Haven't I? Well, never mind. Thought I had done it. Oh yes, I've already done it here. So either they have the same order, so it is has the same form, L to the same m as before, or it should be somewhat larger. So it's the cardinality we have of f equals and it's cardinality of g to the lth. And the cardinality of g was q to l m minus 1, wasn't it? That's here, at the bottom, there. To the lth, and we already saw up here that gives q. What am I doing here? L in mth. I believe this solves part B. I know a little about L-adic numbers, so I should be able to construct an isomorphism between the additive group of ZL, that's the integers, and the Galois group over FQ of the field of extensions generated by all nth power division points. They all have the form of multiplying a certain root with a generator, or I guess you know what I mean. We have no more space here. So we have L roots, L squared root, etc. And I believe all the if we take a generator of the L to fourth, and then we have to multiply all the larger ones as well by G, if we want to multiply with it. But these guys should not be multiplied. We call this generator G4. We must have a generator for each of them. That gives me a representation. What was the problem, really? Let's be more specific about the Galois group. Let's call it they can of course be combined so that we multiply all of these with G4, and then another guy G6 operates on all from here on up. Would be a nice thing to check with this example I have here. Here we have an element of order 9, and if we move these elements, say double them, then we have to double this guy as well. That is, if they lie in FQ to some power of L, then it's already defined. Then we don't have any freedom. As you can hear, I have a loose idea on what to do. So an integer can be written x0 plus x1p plus xnp to the nth, where xn lies between 0 and p minus 1. That's the representation of the p-adic integers. And I would like to map them directly to how we should multiply the element in this group. A loose idea, and as usual I can't make it work without looking at it at my leisure without recording. Good morning. It's now the next day, and I think I've solved my problem. It turns out that it was a misunderstanding regarding the degree of these spaces of each other. So let's just take the most simple example. P equals 2, Q equals 4, and L equals 3. I believed firmly that the degree of this extension was 64 divided by 4, 16. And I believed firmly, where did I have it? In the first part of the video, I believed firmly as well that it was 3. Those two values didn't collide until I came to part C of the problem. But as soon as I got aware of having both opinions, I shut down the video because that was too confusing. Of course, this is wrong. I'm sure you know that, but I didn't. It's actually the logarithms 3 divided by unity. And if we have a generator of the multiplicative group, and then must find an element of order 3. It has order 36, so we take G to... Oh, there's already an element of order 3 in here, so we need an element of order 9. That's G to the 7th. So that's the Galois group. That's a capital G. It has 3 elements, and it must be generated by some map of, say, G to the 7th to G to the 14th or G to something else. We should use what we already know, and that's to apply the Frobenius automorphism. And we need a guy that's constant on F4. So let's apply the Frobenius automorphism twice. It's constant on F2. Of course it's constant on F2, but it's constant, H is constant on F4, but obviously not here. And just to see it happening, H of G to the 7th equals G to the 28th, which is another element of order 4. And F4 is a subfield of F64, is generated by G to the 15th. I don't know. 63 divided G to the 21st. So I think G to the 21st generates, I'll just write it specifically. And then it's obvious that G to 27 is still an order of, is still equivalent to G7. All right. So let's go back to my idea here. I think, yeah, let's assume first that all of these fields introduce one new root. Then thinking becomes more easy, but it's actually the same. I know this because I've recorded this, or I've said this another time today. I just didn't get started the video. I don't know why it didn't start recording, but it didn't. So this is the second time I do it today. If we go from m equals naught to some minuscule m larger than naught, we call it g m. And then have an element, an integer, p-adic integer, l-adic integer. Oh yeah, I corrected that during the first non-recording. Changed this to L. I think I wrote P on the first video. X plus x1L plus x ml to the mth. Then we use the map H, which is the Frobenius operator, to the nth power. And then we map I to H, as finite, and of course we can expand it. Oops. Yeah, in x mth. The point of this is that, oops, that was wrong. No, that's right. X, all of these are constant on FQ. This guy only works on Q in L, where m is unity. These are the identity, all of them, in this field. And L in second, only these two guys work. L in L to the third, only the first three guys work. And that means whatever comes after doesn't work on these. So if we have an infinite expression here of a p-adic integer, then only the first part will work on this. And that means that on this limit, we could take the limit of putting all the guys, extending it with all the guys here, and working up to a finite sum. Only a finite number of them would work. And since it's the limit of the finite sums, every time we take an element here, it lies in one of the finite sums, and then we can compute how it works. And if it turns out that there are more roots in one of these guys, it doesn't matter, the same argument will hold and we will come through the same way. The interesting part is that this misunderstanding I told you about was what alienated me so much to this problem. I guess the finite conclusion is that maybe there's not life on Io yet.